Hi, welcome back. In this slice of physics, we're going to continue our work on circuits. Specifically, we're going to look at resistances in series, which is one of the arrangements for resistances in a circuit. We will address questions like, what is the series arrangement for resistances? How do we recognize it? What can we learn about current and potential for resistances in series? What is the equivalent resistance when you have multiple resistances in series? And finally, how do we use or verify Kirchhoff's law in such circuits? Let's first discuss the arrangement that would qualify as resistances in series in a circuit. As you might expect, if I have a circuit segment that looks like this, and let's say I have a 1 ohm resistance, a 2 ohm resistance, and a 3 ohm resistance, these three resistances are in series. They are next to each other, lined up one after the other. But now let me give you a circuit that looks like this. I've got a battery, I got a resistance over here, and I got another resistance over here. What's the arrangement now? Are these resistances in series? Well, the other arrangement we're going to discuss is resistances in parallel. And initially you might be tempted to say that these two resistors are in parallel since they are on parallel lines next to each other. But in fact, these two resistances are also in series. So we need a better working definition of knowing when resistances are in series. So a good working definition for resistances in series is that there is no junction between the resistances. What I mean by that is the wire continues from one resistance to another with absolutely no alternate path for the current. So when you have such a situation, you will have the same current going through both the resistances. Same I through the resistances. These are better definitions of what resistances in series are and not just how it looks. This circuit is exactly equivalent to this circuit over here, as long as the numbers of the EMF of the battery and the resistances are the same. These two circuits are the same because this is simply an ideal wire that's connecting the two resistances. And so it doesn't matter how long it is or how it bends, whatever current goes through one must go through the other, and that's what tells us that these resistances are in series. Okay, now that we have discussed that, let's take an example of a circuit and learn how we will work with resistances in series. So here's the circuit I've been given to analyze. There's a 9-volt battery with the positive end over here and the negative end over here, so the direction of current is going to be like this in this circuit. And the current goes through two resistances, R1, which is 4 ohm resistor, and R2, which is a 2 ohm resistor. And we want to analyze this circuit to figure out what this current is, what the potential difference across each of these resistances is, and so on. So first we look at the arrangement and verify that this is a series arrangement, which it is. There is no junction between the two resistances, so whatever current goes through one must go through the other by conservation of current. Next, we want to find the current through these resistances. Now you're familiar with the equation of Ohm's law that says I equals delta V over R. And there's a temptation of students to plug and chug in physics. So when you see this equation and you see potential difference there and you see resistance here, there is a temptation to say I1 equals delta V, which is 9 volts, over resistance is 4 ohms. That's what I've been given for R1. And so that gives me 2.25 amps. And I2, once again, plug and chug, delta V is 9 volts. That's the only potential difference I've been given in the problem. R in this case is 2 ohms for R2. And so that would give me 4.5 amps. And based on our discussion that we've just had, you already know that this is not correct. It's wrong. Why is it wrong? Well, you got two different currents going through each of these resistances, and that's not possible. There is no junction between them, so all the current that goes through one must go through the other because of conservation of current that was discussed in a previous video. So we got to look at this a little more closely. And by the way, why did I get misled by this plug and chug? What mistake was there? Well, this equation tells you that current in a resistance equals the potential difference across the resistance divided by the resistance itself. That's the correct interpretation of this equation. And when we put 9 volts here blindly, we're assuming that the potential difference across this 4 ohm resistor is 9 volts. And we know that that's not true. The potential difference across the battery is 9 volts, which means the total potential difference across both resistances is 9 volts. But it's not all taken by just this one resistance, as we will see as we work through this in more detail. So to do that, let me identify some points in the circuit. So I'm going to call this point A. Point B is just before I enter resistance 1. Point C is between the two resistances. D is after resistance 2. And E is just before entering the negative end of the battery. So we want to look at what the potential drop across that first resistance is. So we want to know what delta V BC is, which is the potential at C minus the potential at B, which, as we saw in the previous video, is minus I, which is the current that's going through that resistance, times the resistance itself, which in this case is R1. And I can look at similarly the potential drop across the second resistance, delta VCD, and that'll be equal to current through that second resistance. And since they're in series and there is no junction, that current is also the same I that I had before, times the resistance of the second guy, which is R2. And then the delta VEA is plus 9 volts. That's given to us because that's the potential increase as I go across the battery. And then just to complete the rest of this, delta VAB is 0 because I just have ideal wires there, and as is delta VDE. This segment has no potential drop, this segment has no potential drop because they're just ideal wires. So now let's use Kirchhoff's loop law and say that the sum of all of these has to be 0. So according to loop law, I would get minus I times R1 minus I times R2 plus 9 volt plus 0 equals 0. And when I rearrange these, I would simply get I times R1 plus R2 equals 9 volts. Why is all this important? Well, one of the ways we solve these circuit problems is by taking multiple resistances and turning them into a single equivalent resistance. So I will take the circuit which has two resistances, and let me clear this erroneous work to create some room. So our goal is to take this circuit and turn it into a circuit which has a single resistance because we know how to work with that more readily. But that single resistance has to be the equivalent resistance of how both of those in series behave. So I still have the 9 volt battery and I have only one resistance. So in this case, the potential difference across the battery and the potential difference across the resistance are the same because all I have in between there is ideal wires and there's no potential drop there. So for this equivalent circuit, if I apply Ohm's law, I would get the current I, and if it's an equivalent circuit, it's got to be the same current as in this circuit. So I would simply be equal to delta V R over R, where delta VR is the potential drop across the resistance, which in this case is 9 volts divided by R equivalent. And I can rearrange this to write I times R equivalent equals 9 volts. So now when I compare these two things, and since I is the same on the left hand side and 9 volts is the same on the right hand side, whatever I is multiplied by in both of these cases have to equal each other. So from that I get R equivalent equals R1 plus R2. And that's a key takeaway for resistances in series. When you have multiple resistances in series, the equivalent single resistance they represent would simply be the sum total of all those resistances. And if I had more than two resistances, I would simply just add the others as well, R1 plus R2 plus R3 plus R4, and so on. So given that we have seen the justification for this, now let's use this and see how this circuit can be analyzed. So in our case, this R equivalent would simply turn out to be 4 ohms plus 2 ohms, which would be 6 ohms, which then would give us the current here through this circuit, I, as 9 volts divided by 6 ohms, which is 1.5 amps. So I've got a 1.5 amp current going through this circuit, and since these circuits are equivalent, I've got the same 1.5 amps going through this circuit as well. So now that I know the current, and this is 1.5 amps, which was not a simple plug and chug off the Ohm's law, but I had to think about it, figure out what the equivalent resistance was, and use that to get the current. Now I can figure out delta VBC and delta VCD. So let's do that. Now delta VBC is the potential difference across that resistance. That's minus I, which is the current through that resistance, times R1, which is that resistance itself. And now I know all of these. So this becomes minus 1.5 amps times 4 ohms, which is minus 6 volts. And delta VCD similarly would be minus the current through that second resistance, which is also the same I, times R2, which is that resistance, and that equals minus 1.5 amps times 2 ohms, which gives me minus 3 volts. So this is why our simple plug and chug would not work, because the potential drop across this first resistance is not 9 volts, it's 6 volts. The potential drop across the second resistance is not 9 volts, it's 3 volts. So there we have it. We have solved for the current through both these resistances, and we know the potential drop across each resistor. As a final step, let's verify Kirchhoff's loop law for the numbers we got. So the delta V loop starting at point A would be delta VAB plus delta VBC plus delta VCD plus delta VDE plus delta VEA. Okay, now I know all these numbers. Delta VAB is simply 0, ideal wire. Delta VBC is minus 6 volts. I figured that out over here. Delta VCD is minus 3 volts. Delta VDE is 0. Delta VEA is plus 9 volts. And so all of that is minus 6 minus 3 is minus 9, plus 9 is 0. So my Kirchhoff's loop law is verified. So in this slice of physics, we work with resistances in a series arrangement. We first got to know how to recognize the series arrangement, and then we realized quickly that the same current has to go through all the resistances when they are arranged in series. That was a direct consequence of Kirchhoff's junction law, or conservation of current, which then led us to deriving the equation, or realizing that the equivalent resistance for multiple resistances in series is simply an addition of all those resistances. And once we got all those numbers, we verified that Kirchhoff's loop law works for these circuits.